For this problem, on the topic of kinematics in one dimension, we are looking at the process of designing a rapid transit system. And we want to look at two situations. A train needs to make a 15-kilometer trip, firstly, where the stations at which the train must stop are 3 kilometers apart, which gives a total of 6 stations. And the second situation are where these stations are 5 kilometers apart, with 4 stations in total. If we have the acceleration of the train, the maximum speed that it can reach, and then the deceleration, and the time it stops at each station, we want to calculate the time it will take the train to make this trip in both situations. So firstly, we can analyze this problem as a series of 3 one-dimensional motions: the acceleration phase, the constant speed phase, and the deceleration phase. Now, we can first find the maximum speed of the train, which will always be the same. So the maximum speed is given in kilometers per hour, and this is 95 kilometers per hour, and we'll convert this to meters per second. So that's 1 meter per second over 3.6 kilometers per hour. So converting kilometers to meters and hours to seconds. This gives us the maximum speed of the train in SI units to be 26.39 meters per second. Now, in the acceleration phase, the initial velocity v0 is equal to 0, and the acceleration itself is 1.1 meters per square second. Now, we also know the final velocity, so we can find the elapsed time for the acceleration phase. So for the acceleration of the train, we have the final velocity v is equal to the initial velocity v0 plus a times t. So if we rearrange this equation, we can solve for the time it takes the train to accelerate to maximum speed. So t is v minus v0 over a, and this is 26.39 meters per second minus 0 divided by 1.1 meters per second squared. And so if we calculate, we get the time for the train to accelerate to maximum speed to be 23.99 seconds. Now we want to find the displacement during the acceleration phase. So the displacement is x minus x0, and this is for the acceleration phase, so subscript ACC. We know that this is equal to v0 t using another kinematic equation plus a half a t squared, where the time here is the time taken for the acceleration. So that's 0, since the initial velocity is 0, plus a half times the acceleration of 1.1 meters per square second times the time of 23.99 seconds all squared, which gives us the displacement during this phase to be 316.5 meters. Now in the deceleration phase, we know the initial velocity v0 to be 26.39 meters per second. So for the deceleration phase, we know the initial velocity and we know the deceleration, which is minus 2 meters per square second. We also know that the train will finally come to rest, so its final velocity is 0. So using the same equation, we can find the time that the train takes to decelerate to rest. So v is equal to v0 plus at, which means that the time taken for deceleration, t, is equal to v minus v0 over a. That's 0 minus 26.39 meters per second divided by the acceleration of minus 2 meters per square second, which gives us the deceleration time of 13.2 seconds. So now the distance traveled during deceleration is x minus x naught subscript dec for deceleration, and we use the equation again that we used above for the acceleration, v naught t plus a half a t squared. And so that's the initial velocity of 26.39 meters per second times a time of 13.2 seconds plus a half into minus 2 meters per square second, which is deceleration, times t squared, which is 13.2 all squared. And that's seconds. So calculating, we get the displacement covered during deceleration to be 174.1 meters. So the total elapsed time t is equal to the time for acceleration plus the time for deceleration, or the total time for the acceleration and deceleration phases, and that's 23.99 plus 13.2, which gives us 37.19 seconds. We just add the two times calculated above. The total displacement for these two phases, x minus x naught ACC plus the displacement covered during deceleration, x minus x naught DEC, is 316.5 plus 174.1, which gives us 491 meters. Now let's look at the first situation where the stations are 3 kilometers apart. So if the stations are spaced 3 kilometers apart, which is 3,000 meters, then there's a total of 5 interstation segments, 15,000 meters, which is 15 kilometers, divided by a spacing of 5,000 meters, or by 3,000 meters rather, gives us 5 interstation segments. So a train making the entire trip would have a total of 5 interstation segments and 4 stops of 22 seconds each at the intermediate stations. Since 491 meters is traveled during acceleration and deceleration, we can take the distance of 3,000 meters minus 491 to get each segment traveled at an average speed, an average speed of 26.939 meters per second. So 3,000 meters minus 491 meters gives us 2,509 meters. And the average speed is 26.39 meters per second. That's for the distance of 2,509 meters. The time for that 2,509 meters we get from delta x, we know, is the average velocity times delta t, v bar delta t, which means that the time at constant speed, we'll call it tc, is equal to delta x over the average speed, v. That's 2,509 meters divided by 26.39 meters, or meters per second rather. This gives us the time at which the train travels at constant speed to be 95.07 seconds. So a total interstation segment will take the following amount of time. .19 seconds plus 95.07 seconds, which gives us a total time of 132.26 seconds. Now, with 5 interstation segments of 132.2 seconds to 6 seconds each and 4 stops of 22 seconds each, the total time, we'll call it T3 for T of 3 kilometers, is equal to 5 into 132.26 seconds plus the time for the stops, which is 4 times 22 seconds, which gives us a time of 749 seconds, which works out to 12.5 minutes. So that's the time the train will take for the total trip, where the distance between the stations is 3 kilometers. So now let's repeat this process for the stations being 5 kilometers apart. So 5 kilometers is 5,000 meters. So 15,000 divided by 5,000 gives us 3 interstation segments. So a train making the entire trip would have 3 interstation segments and 2 stops of 22 seconds each at each of the intermediate stations. Now we know 491 meters is traveled during acceleration and deceleration. So 5,000 meters minus 491 meters gives us 4,509 meters of each segment is traveled at an average speed of v is equal to, similar to above, 26.39 meters per second. Now the time taken for the 4,509 meters, we get by d is equal to v bar times t, like before, which means that t is the distance divided by the average speed, d over v. And so this is 4,509 meters divided by 26.39 meters per second, which gives us a time of 170.86 seconds. So a total interstation segment will take a time of 37.19 seconds plus 170.86 seconds, which is 208.05 seconds. So with 3 interstation segments of 208.05 seconds each and 2 stops of 22 seconds each, the total time for the trip where these stations are spaced 5 kilometers apart, T5, is equal to 3 into 208.05 seconds plus the time for the stops, which is 2 times 22 seconds. This gives us a total time of 668 seconds, which works out to 11.1 minutes.